best practice number 1, put numbers to your gut. We had this customer come to us for consulting, and they had a certain chemical process that goes on inside an enclosure, and they were using a gas to feed that process. Now, we signed a non-disclosure agreement with them, so I can't tell you the customer's name or even the process or even the gas they used. But they were making a new product, and they were going to make it just like all their old products, where they had a big feed system from their gas tank into their chemical tube. And they brought us in just to make sure to check, let's see how much gas we need. We think we know how much gas we need, but this product's going to be smaller than our previous product, so let's just do a check. We did one flow study, and we found out that the amount of gas they needed, when the gas comes in, it'll spread out through the chemical process and go out through holes in the bottom, right? That's their theory. That's what they had in mind. We did one flow study, and we found out that the amount of gas they needed was 500 times less than what they thought it was going to be, right? I wouldn't have believed this if I wasn't in the meeting when Keith presented the numbers, but it was about 500 times less. Why is this? Well, I can't tell you again because we signed the non-disclosure agreement, but think about the difference between a garden hose and a capillary action, right? They're different types of physics. So by making their product smaller, by changing some other things inside their enclosure, by changing some other smaller things, they, without knowing it, had moved into a different realm of physics. And that's why the flow simulation said they'll need 500 times less gas than they would have previously. And when in that conference room when we presented this, their managers were amazed, and they started thinking, they're like, oh my God, that means we don't need the gas tank. That means we don't even need this huge, delivery system. We could have a tiny little gas tank attached to our product. What does that mean? Well, now our product's mobile. Now we can move it around. Now we don't need to hook into the shop lines. Now we can put it in the back of a truck and move it around. Right? All these new ideas started coming out, these blue ocean ideas, because of what one flow study did. They had a gut feeling that they needed less gas. They just didn't know how much less. Right? And now they can do things their competitors can't even think about because they put numbers to it. Right? Put numbers to your gut. One other way that's a good example. Let's look at a sad example. The de Havilland Comet was a passenger plane made after World War II, and it was trying for blue oceans as well. It was the first aircraft with an all-metal skin. It was the first pressurized passenger aircraft. It was going to fly 2 times faster, 2 times higher, 2 times farther than any previous propeller-driven aircraft. Right? It was the first jet passenger. It was going to usher in a new era of luxury jet travel. Well, it did. They designed it. Lots of fanfare. People started using it to go around the world. But then when it got to about 1,000 flight hours, one of them broke up and fell in the ocean. Did an investigation, nothing really conclusive. Second comet got to 1,000 flight hours, broke up, fell into the ocean. Right now things are getting serious. The third one did it, they shut the whole line down. They did some research and they figured out why. But if you look at this picture, you can actually tell what the problem is. Al, can you see the problem with this aircraft just from looking at this picture?
I'm looking at maybe the wings, the attachment point of the wings.
Maybe. When I presented this at a user group, one person said the wings, or the fact that the engines are in the wings. That's a good guess, but not yet. It's a more subtle thing, but you can definitely see it in the picture. What's weird about this aircraft that you don't see in other aircraft?
No. Yeah, I'm still losing it.
No, that's fine. This is fine. I presented this in front of 30 people, 30 engineers at a SolidWorks user group, and only one of them got at the very end.
I think the answer is that we didn't have simulation back then.
Well, no, the answer is, that's a good thinking. The answer is you don't see a lot of square windows on aircraft, do you?
Ah, good point. They're all round.
They're all round. De Havilland Comet has square windows. And of course, when they did the investigation, that's what they found out. The windows were stress concentrations, caused fatigue cracking, caused the planes to crash. But the people who made the Comet, they weren't dumb engineers. These were the guys who had made the bombers for World War II, some of the best engineers in Britain. They knew about stress concentrations, right? And in fact, that's the first thing they tested when the first plane went down. But what happened in this case? Well, if we make up this in SolidWorks here, if we take a sharp corner, there, put some pressure on the inside, you can see some stress, and we put different radii, we can see the stress go down. A radius of 2 inches, 43% lower than the sharp corner. 5 inches, 73% lower. 10 inches, 78, not that much of a difference from the 5 inches. Here's what happened. When they dredged these fuselage off the bottom of the ocean, and they started doing some testing, maybe on some new planes as well, they put strain gauges around the corners of these windows, and the numbers they found surprised all the design engineers. The stress was 2 to 3 times higher what the designers expected. So what happened is the designers had a gut feeling. They knew that infinitely sharp corners were bad, right? They weren't dumb, but they put some radii on there, and they thought they were in this range. They thought the stress was a lot lower than the sharp. They were actually in this range up here, right? The stress is maybe only half as low. And if they'd put some numbers to their gut, like Al was saying, if they had run a simulation study or had a way, obviously back then in the 1940s, they couldn't run simulation. But if they had put some numbers to their gut, they could have easily seen that, well, going from sharp to 2 inches is a big decrease, half the stress. Going from 2 to 5, another big decrease. Going from 5 to 10, not so much of a change, right? So 5 is kind of the place you want to be around. It's the most bang for the buck. All right? They knew what was wrong. They just didn't have numbers when they went into that blue ocean. All right? So that's best practice number 1. Put numbers to your gut instincts. If you're going out into a blue ocean, you need a map, and that map has to be to scale. Put numbers to your gut.